Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be solving a Harvard exam from MIT, and the question reads: show that 1 plus 1 on 2 times 2 plus 1 on 3 times 4 plus 1 on 4 times 8 plus 1 on 5 times 16 right up till forever is equal to 2 times ln 2. So this problem is very technical because we are going to be using so many concepts which is going to marvel you, so stay tuned as you watch. Okay, so the first thing we are going to do is that we are going to find the end term of the series. All right, then we now have to look for the sum to infinity of that end term. You realize that this is not an AP, this is not a GP. If it was a GP, it's going to be very easy for us to find the end, to find the sum to infinity, provided it converges. But sure, it's not going to be a GP because this is 1 over 4. If you take 1 over 4 divided by 1, you get 1/4. Now this is 1 on 12. 1 on 12 on 1 on 4 is 1/3. You realize that already there is no common ratio because the ratio of two consecutive terms, as we have seen, are all different. So automatically from there you can clearly see that this is not a geometric sequence, as well as it is not an arithmetic sequence. Okay, because if you take 1/4 minus 1, it's not going to give you 1 on 12 minus 1/4. So from there you realize that the problem is very complicated. But anyways, by the end of the video you realize that the problem is not that too complicated. Okay, now what we are going to do is that we are going to start by finding the end term of the sequence that we are summing. All right, now the numerator has no problem because it's constant. The numerator is just ones. All right, so we have to focus on, okay, what is the end term of the numbers in the denominator? So what we are going to do is that we are going to find two end terms and we multiply. All right, we are going to find the end term of 2, 3, 4, 5, and so on and so forth. Then we find the end term of 2, 4, 8, 16, and so on and so forth. Then we multiply the end terms to have the end term of the denominator. But now we have to also consider the first term. So we have to kind of impute an invincible 1 in the denominator of the first term. So we are going to have something like 1 times 1. Okay, because that's the only thing we can put there. Those are the only two whole numbers you can put there to still give us everything as being 1. All right, so we first of all start by finding the end term of the numbers of the first numbers that are being multiplied, which is 1, 2, 3, 4, 5, and so on and so forth. It's very easy because 1, 2, 3, 4, 5 are basically following an AP whose end term is n, because the common difference is 1. So the end term is equal to T of n. T of n is equal to 1. T of n is equal to n for all n greater or equal to 1. So that's the end term of the numbers 1, 2, 3, 4, 5. When n is 1, we have 1. When n is 2, we have 2. When n is 3, we have 3. When n is 4, we have 4. When n is 5, we have 5. But we can also have the next term. When n is 6, we have 6. Now, what about the numbers 1, 2, 4, 8, 16? What do they follow? They clearly follow a GP because 2 over 1 is 2, 4 over 2 is 2, 8 on 4 is 2, and 16 on 8 is 2. So we can conjecture that these numbers follow a GP, and the end term of a GP is given by a arrow to the n minus 1, where a is a first term and arrow is a common ratio. Our common ratio is 2, so the end term is 2 to the power n minus 1 because the first term is 1 for every n greater or equal to 1. So in essence, this sum is equivalent to the sum from 1 to infinity of T of n times u of n, because the denominator, 1 over T of n times u of n, because the denominator is basically following the sequence T of n times u of n. So this sum here is just going to be the sum from n equal to 1 to infinity of 1 divided by T of n, which is n, times u of n, which is 2 raised to the power n minus 1. So this is the very first step we have to carry out to be able to proceed with the solution. All right, so from here now we now start kind of simplifying and getting results that we want. So I will start by writing 2 to the n minus 1 as 2 to the n times 2 to the negative 1, then sending 2 to the negative 1 to the numerator to become 2 to the power 1, then removing the 2 out of the sum because it is a constant, we arrive at this position. So in essence, this sum is equal to 2 times the sum from n equal to 1 to infinity of 1 divided by n times 2 raised to the power n. Okay, now in the previous slide, we ended at 2 times the sum from n equal to 1 to infinity of 1 on n times 2 raised to the power n. Now from here, I'm going to use a very technical property which is very applicable. Okay, so we are going to introduce integration in this sum. All right, so what we are going to do is that I'm going to give you a generalized integral, which is the integral from 0 to a, where a is a real number, of x to the n minus 1. Normally, if you integrate x to the n minus 1, you're going to have x to the n divided by n. I'm doing that because I'm seeing a division sign by n here, and I'm seeing a number raised to the power n, so I have to think about this integral. So the integral of x to the n minus 1 is basically x to the n over n. All right, now if you input a limit from 0 to a, when you input the lower limit, you will get 0. So the final answer is just inputting the upper limit and simplifying. And when you input the upper limit as x, you are going to have a raised to the power n divided by n. Now look at 1 over n times 2 raised to the power n. You realize that if you compare 1 over n times 2 to the power n alongside with a to the n over n, the n's are already in the denominator. So what we are left with is just with this a to the power n that is in the numerator. All right, but we can send it to the denominator if a is a fraction, basically 1 over a certain number. All right, so if I just let a to be equal to half, you realize that half raised to the power n over n is equivalent to 1 over n times 2 raised to the power n. Very equivalent. You can use your pen to verify that. So basically, I'm going to write this. I'm going to write 1 over n times 2 to the power n as well, the integral from 0 to half of x to the n minus 1 dx. We have clearly seen that this integral from 0 to a will give us a to the n over n. So if a is equal to half, then we are going to have half to the n over n, and half to the n is the same as 1 over 2 to the n. Then that 2 to the n meets n in the denominator. So the integral 1 over n times 2 to the n is equivalent to the integral from 0 to half of x to the n minus 1. Now there's what we call the convergence theorem. Now it says that the sum of an integral is the same as the integral of the sum, and vice versa, but provided there is divergence, or provided there is convergence. We clearly see that this integral converges, it gives us a value. All right, and definitely the sum of the integral will give us the integral of the sum. All right, so from here you realize that if we want to sum x to the n minus 1, we are basically summing a GP, and since the interval is from 0 to half, the common ratio is basically the common ratio of that GP is equal to x, and for a GP to converge, the absolute value of the common ratio has to always be less than 1. All right, so since x is in the interval 0 to half, the absolute value will definitely be less than 1, so the convergence theorem is going to hold. So from that convergence theorem, this sum on the left hand side, which is our original sum, will just be equal to the integral of the sum. Remember, the sum of an integral becomes the integral of the sum. So we are going to have the integral from 0 to half of the sum from n equal to 1 to infinity of x to the n minus 1. Then when we get the sum, we have to integrate it with respect to x. That's why you see find a dx here. Clearly, this is the sum to infinity of what? A GP, all right, whose first term is x to the power 0, that is 1, and whose common ratio is x. When you find a common ratio, so at the end of the day, the sum converges because x is in the interval 0 to half. So when the sum converges, you realize that you just have 1 over 1, a over 1 minus r as the answer of the sum. A is 1 and r is x, so we are going to have 2 times the integral from 0 to half of 1 over 1 minus x, and we need to integrate with respect to x. Remember that 1 over 1 minus x is basically what this sum gives. All right, now if we integrate 1 over 1 minus x, we are going to have negative the ln of 1 minus x, the absolute value of 1 minus x, but there is a 2 here. Then we need to impute the bounds from 0 to half. If I impute 0 as my lower bound, I'm going to have negative 2 the ln of 1, and the ln of 1 is 0, so the lower bound will give us 0. If I impute half as my upper bound, I'm going to have negative 2 the ln of half, but the ln of half is the same as the ln of 2 to the negative 1. The negative 1 meets the negative 2 here to give us positive 2, and at the end of the day, the final answer gives us 2 times the ln of 2, and we have come to the end of this video. Thank you guys for watching, and see you guys in the next video.